Hello everyone and welcome back to the RBT Security YouTube channel. This is part 3 of our Kubernetes penetration testing series. In part 1, we breached a vulnerable web application. In part 2, we escalated our access through Docker SOC. In this video, we will demonstrate how to escape a compromised container and take control of the worker node. We will achieve a reverse shell by exploiting the privilege flag, which is a dangerous misconfiguration that it is all too common in real-world environments. Before we begin, if you are new here, please hit subscribe, give us a like, and leave a comment about which adversary emulation topic you would like us to cover next. Your support helping us to create a straightforward real-world offensive security content. Remember, every click counts. Let's recap. In part 1, we began with the web application exploit that provides us with the initial access inside a container. In part 2, we exploited Docker SOC to compromise the worker node file system. Today, in part 3, we will explore another approach, breaking out of a privileged container to take control of the worker node, getting a reverse shell. Before to continue, we have to discuss about privilege flags. What is privilege flags? When privilege flags is used with a container, it gives it all Linux capabilities to the container. capsys module, capsys admin, capsys ptrace are some of the dangerous capabilities. If an attacker gains access to the container with capsys module enabled, the attacker can load malicious kernel module directly into the host kernel. This can lead to privilege escalation, persistence, system compromise. We will explore a new vulnerable web application. This time, the vulnerability is known as server-side template injection, which allows for code execution. The first step is to start executing simple payloads and see how the web application reacts. As you can see, the web application is rendered and responded to our malicious payloads. It looks like we are operating under the root context. And even we were able to retrieve the content of the etc pass.wd file. We confirm that the command has been executed and now it's time to get our initial foothold. We will spawn a reverse shell using a simple Python payload. The first step is to set up our first listener using netcat. In this case, we are going to use the port 5555. And let's execute our malicious payload. And look at that. As you can see, we successfully managed to retrieve a reverse shell. Before to proceed, let's improve our shell. We now have remote access to the container. Let's check for misconfigurations. One of the ways to check for secure flags is using the capsh command. We are interested to see this particular capsys module. It looks like it's enabled, which is a good sign. We confirm that we have elevated kernel capabilities. we are operating in a privileged container, which allows us to delve deeper. Before compiling the kernel module reverse shell, we need to make sure that the operation system has the same kernel version of the container. So we can achieve that by using the uname our command. And in this case, we are using a second virtual machine to compile the kernel module. And as we can see, both of them has the same kernel version. This is very important, otherwise the kernel module will not work on the container. So the next step is to clone the reverse shell, which will be available in our GitHub repository. Can clone it. After cloning the repository, the next step is to compile it, insert this module and spawn a reverse shell, this time from the worker node itself. We can use the command make clean and make to obtain our reverse shell. And look at that, as we can see, we successfully compile our kernel module. We need to transfer our kernel module to the container, so we can use Python server along with the wget command. It's time to load the kernel module and establish a new reverse shell. Before we proceed, we need to set up our second listener, this time in a different port. For this demo, we are going to use a different port, and we are going to open a new terminal, login into our Kali machine, and set up the listener. We are going to also open a new terminal to log in into our worker node. Perfect. So once we have everything set up, the next step is to load the kernel module and obtain our second reverse shell. So we can do it using the insmode command. And as we can see, we successfully managed to get our second reverse shell from the worker node. To verify container escape, we access a file that only exists on the worker node root file system. In this case, we are going to try to cut this file, docker worker sock bool crackmeat.txt. and this is the content. We are going to prove that and the worker system. We are going to move to the root folder and cut the same file. And it looks like the content match. Lastly, we can obtain the IP address of the worker node to confirm. It looks like the IP match. The IP is 192.168.115.134. So that confirmed that we have successfully broken out of the container. In part 3, we show how attackers can chain web vulnerabilities with Kubernetes misconfigurations to fully compromise nodes. In part 4, we will concentrate on lateral movement. We will explore resource-based access control, abuse, and demonstrate how attackers can escalate from container access to complete master node control. Thanks for watching. Like, subscribe, and follow RBT Security for more advanced hacking content. See you in the next one.